This is lecture number 26. In this lecture, we are going to learn the irrigation wells. So, this week and the following week will be concentrating on some information from irrigation wells as well as irrigation pumps. Okay, so, because these are important when you are talking about extracting water or water to the field. So, we have seen how to get water from canals. So, now in the locally if you have some water sources like in irrigation wells. So, still we need to understand how to get the water from irrigation wells for the irrigation purpose. Okay, so, here, so in order to understand that we need to know the soil formations and what are the different soil water zones just to understand and what is an aquifer, what is not a good aquifer, right, and the aquifer properties. Okay, so, in this lecture we will be focusing on the aquifers and their properties. Okay. So, now see here the soil water zones. So, if you start digging the soil from the surface, right. So, you can observe different zones. Okay. So, the first zone here if you see, so the first where the crops are grown. So, this zone is called soil water zone, right. So, this is as far as crop production is concerned, this is important, this zone. And then, so this is the soil water zone. Okay. So, then below that there is intermediate zone and then fringe water zone, okay, and the groundwater and internal water. So, if you take a profile like this, okay, so here generally, so there is a groundwater where the soil is completely saturated. So, if you dig hole in this particular point, right, and definitely you get water. Okay. So, and if you make half of this, for example, so this is the water groundwater, and above this is the surface, okay, this is the plant, and the first zone here you see the soil water zone, right, and the second is intermediate zone, and this is a capillary zone because the groundwater can move upwards due to the capillarity. Okay. So, so these are the main zones, the first soil water zone, intermediate zone, capillary fringe zone, groundwater, and this is internal water. So, this is not accessible for usage. Okay. So, then again, so this is called belt of soil water, and this is intermediate belt, and this is the capillary belt. Okay. So, and so this whole thing from here to here. So, since it is the soil pores are not filled with water and every time. So, that is called suspended water, right, suspended water, or the zone of aeration. So, this is called zone of aeration because the pores will have air in it, okay, both air and water in it. Whereas, there is another zone, this is called zone of saturation. So, where you see the pores are completely filled with water. So, that is a zone of saturation. Okay. So, and from here to the zone of aeration, this is zone of aeration, it is also called the vadose zone. Okay. So, vadose zone is unsaturated zone. So, which starts from the, land surface to the water table. Okay. So, that is the complete zone of aeration, okay, vadose zone water. So, then so this is called the zone of rock fracture. So, where the water is available, and the zone of rock flowing. So, this water will not be available for utility. Okay. And okay. So, this way at least we understand the what kind of water which is present in the soil. So, the first is soil water, intermediate zone, and capillary fringe, groundwater, and then this is unavailable deep deep groundwater zone. Okay. So, so here the top of the saturated zone or groundwater zone is called the water table. So, water table is the top of the groundwater zone. So, that is called water table, and this water table is influenced by atmospheric pressure. So, directly you can have the influence of atmospheric pressure, because this soil is not completely filled with water. So, there is a atmospheric interaction to this zone. So, the pressure at the water table is equal to the atmospheric pressure. Okay. So, again the groundwater, if you see, so the volume of weather zone below the soil moisture zone is estimated to be around 10,000 mile cube. So, which is potential groundwater recharge. Okay. So, which is a potential groundwater recharge. So, here what we are expecting up to this, whatever water which is stored in the weather zone will be contributed to the groundwater recharge, and that will be estimated as 10,000 mile cube. Okay. And then, so the next, if you see the soil water zones further, the zone of aeration is acts like a filter. So, if you remember, so we have like this is zone of aeration and zone of saturation. So, zone of aeration which acts like a filter for the rainfall. Rainfall infiltrates down, and this is the filter meter, this is zone of aeration, and recharge to the groundwater. Okay. So, from the water table, if you go below 0.5 miles, so that accounts about 1,000,000 mile cube of groundwater. Okay. And that will be around 3,000 times greater than the volume of water in all rivers. So, it is a huge amount of water which is lying as groundwater, okay, which is below 0.5 miles from the water table. And the groundwater below 0.5 to 5 miles is not recoverable. So, this is simply lying over there, and it is not accessible or not recoverable. So, okay, that is, and the groundwater accounts nearly 2/3 of the fresh water, and groundwater flows very slow. So, it is like 10 to 15 meter a day. So, that means if you have 10 meter distance or 10 meter, let us say a room having 10 meter length. So, it takes a day to flow from one end to the other end. And the great depth, the water may takes 1,000 years. Suppose if you have a great, if you go deeper, see the 1,000 years it will take, and that passes through aquifer and sometimes completely stagnant. Okay. And next is, so this is a simple example to see how the water availability will be used for the existing population. So, assume that world's recoverable groundwater is this much, okay, and how long will this water be able to meet the needs of the world's population? Say 5 billion. We have 5 billion population, and so how long this amount will be useful for the 5 billion people. So, the 5 billion, if per capita daily consumption is taken as 4,000 liter, okay, per capita daily consumption is taken 4,000 liter. So, let us say world population is 5 into 10 power 9, that is 5 billion, and per capita daily consumption is 4,000 liter, and total world daily consumption is population and per head. So, 2 into 10 power 13 liter per day is a total world water consumption per day, and the total groundwater supply is 4 into 10 power 6 kilometer cube. You convert that into liters, you get this. Okay. So, now you divide, right, divide this by this, you get 2 into 10 power 5 days, you convert that, it takes 548 years to deplete or utilize the entire water reserve for the 5 billion population. Okay. So, next is the what are the type of geological formations. So, if you go down, because water is there. Okay. So, the water is there does not mean that it is available always. Okay. It all depends on the media, okay, the porous media. Suppose if you have, so porous media in the sense this is soil type we are talking about. So, if you have sand, if you have clay, if you have silty loam, so if you have rock fractions, or if you have solid rocks. So, all these things, so based on the type of particular geological formation, the water availability will be defined. So, for example, the types of geological formations are very important in order to understand whether we be able to get the water from the particular location. Okay. So, here we have an aquifer. So, what is exactly an aquifer? So, each geological formation has a particular property, like so it will, so that is kind of a for example, assume that it is a sponge. Okay. Sponge is a porous material, okay, porous media. So, you add water, what happens? So, it absorbs water, at the same time if all pores are filled, so the water is going to drain due to gravity. Okay. So, that means the sponge can absorb as well as transmits. Okay. So, that is the particular property. So, similarly, the soil or sands or other rock material, they will have a particular property. So, we are going to see whether that property can be I mean favorable for water availability or not. So, here the aquifer, so that means a geological formation which absorbs water and transmits water. So, it has both characteristics. Okay. So, if you have a geological formation, so it absorbs water and transmits water. This is very important though, because where you can extract water, right. So, aquifer is very important in case of extracting water or source of water reservoirs. Generally, the soils like sands or gravel, so there you have a definite pore structure. So, that will be a good aquifer. So, if you observe like the drillers who drills the tube wells. So, they will be keep digging as long as, so every time they started checking the material which is coming out from the hole. Okay. So, then when they see sand, is coming out from the hole, then they think that okay, they reach the aquifer and they stop digging it, and that is it. So, there, so because the sand is good aquifer material where it can absorb or it can take water as well as transmit water. Okay. So, here, so similarly aquifers is a geological formation. Okay. So, it neither absorb neither transmit. So, if you say suppose this is a material, right. So, it cannot absorb, as well as once it is not absorbing, there is no question of getting water from this material. So, this is called aquifers. Aquifers are solid granite. So, if you have a solid granite, right. So, since there is no definite pores, so water cannot penetrate in, that means it cannot absorb and it cannot transmit. Okay. So, these are like aquifers or the bad aquifers, you do not get any water in that formations. Okay. And aquiclude, the geological formation that it porous aquifers, aquiclude is a porous. Okay. So, it only can absorb, but it cannot transmit. Okay. So, contains water, but it is not capable to transmit water. So, that is the aquiclodes. For example, clays. So, clays absorb, right, and it swells. So, once it has water, it started swelling it, and it is very I mean a small quantity can ooze out, but it is really not transmitting, okay, anything. So, this is aquiclode. And aquitard, the name indicates aquitard is kind of a retard. So, the aquifer got retarded. So, that means a good aquifer after a long period of time. So, the sand is a good aquifer. So, having clay particles into welcoming clay particles into the system, so that can block the pores. Okay. So, that acts as aquitard. Okay. So, this aquitard, what happens? So, it also absorbs water, but the thing is it is not going to transmit water, but it is definitely influencing the neighboring aquifers. Okay. So, this is important. So, the geological hydrological conductivity is too small, okay, and permit development of a well or spring, but sufficiently large to influence the hydraulics of aquifer adjacent to it, like sandy clay, etc. Okay. So, these 4 are the important geological formations we need to consider here. Okay. So, the next is the confined aquifer. So, now we are talking about aquifers, aquifer that is a good which can absorb and transmit water. Okay. So, the confined aquifer. So, in this case what happens, if you see this picture. So, there are if the soil layer is present. So, this is the soil layer or reservoir which is present in between the 2 confined layers. So, it is generally impervious layer. So, this is an impervious layer. So, that means water will not pass or water will not enter, water will not pass, water will not enter. So, that means it is confined between the 2 impervious layers. Okay. So, this is called a confined aquifer. So, that means the water or the saturated stratum is under pressure basically. So, definitely if you drill hole into that, that means if you dig a hole or if you put a well into this. So, definitely water will penetrate enters through this, right, like a jet. Okay. Similarly, if you see this. So, this is one impervious surface, this is another impervious layer, right. So, this is the geological formation. So, when you make hole, it is going to come out. Okay. So, this kind of wells are called artesian wells or flowing wells. So, that means this continuously flows. Okay. So, the continuously flows. Suppose if this head, so the pressure head which is more than the level of the well, the outlet at the well, definitely it is going to flow. If the pressure head which is less than the length of the well, right. So, this will be staying here constantly. Okay. This will be staying constantly here. So, that is called, these are, in this case this is called flowing well, whereas in this case this will be artesian well. Okay. All right. So, yeah, here artesian well and flowing wells are there. A rise and fall of water in well results due to the hydrostatic pressure in the stratum. So, rising, falling, it all depends on the pressure which is built up inside the aquifer. This is confined aquifer. Okay. So, the next is unconfined aquifer. So, here if you see the unconfined aquifer case, so the one part is impervious surface, then other part is open to the atmosphere. So, suppose this is the ground level and there is a impervious layer and this is the soil stratum, that means it is completely saturated, right, completely saturated. So, that means this, in this case the pressure which is acting on the stratum is atmospheric pressure, right. this is not confined between two impervious layers, but since this is open to the atmosphere now, right. So, the pressure which is acting on this this is atmospheric pressure. So, in case of unconfined aquifer, so the soil stratum or geological formation will be sitting on the impervious layer, only one side. Okay. And the top of the geological formation is known as the water table here, and whereas the top of the geological formation in case of confined aquifer, it is called piezometric surface or potentiometric surface. Okay. So, here also the rise and fall of the water table results primarily from the changes in the volume of storage in the structure. So, when the piezometric surface fall below the bottom of the upper confined stratum, the confined aquifer becomes unconfined aquifer. Okay. So, in case of confined aquifer, so this is the pressure, right. So, this is the impervious layer, and this is the soil stratum in case of confined aquifer. Suppose if this pressure falls below the stratum, so that means this is not right now it is full and that there is no enough hydrostatic pressure, and then is definitely influenced by the atmospheric pressure. So, then the pressure equipotential line, if you join, that will be equal to the water table, not the piezometric surface in case of confined aquifer. So, when the confined aquifer can act as unconfined aquifer. So, that is because when you are not getting enough pressure in the confined geological formation. So, that becomes unconfined even if it is sitting in between two impervious surfaces. Okay, the next is the perched water table. This is a localized condition. If you see, for example, there are clay layers which are formed in locally. So, since it is a clay layer, for example, this is a clay layer, and so the water which will be stored here, just like your unconfined aquifer, okay, just like unconfined aquifer. So, since it is a locally formed, so this is called perched perched aquifer, and this is called perched water table. This is perched water table because the water table is influenced by atmospheric pressure here. Okay. So, here if you see, so this is unconfined aquifer, this is the unconfined aquifer, and this is the water table, whereas this one is the local unconfined aquifer or perched water table or perched aquifer, and it has also have a water table. Okay. So, if you drill hole here, so water will be available up to this. If you drill hole here, so this is connected to the unconfined aquifer, and since this is the water table, so water will be seen at this point. Okay. So, this is basically formed due to clay or any sediment deposits. Okay. Okay, the next is leaky aquifer. Okay. So, the other one is leaky aquifer. So, here in case of confined aquifer, if you see, there is a impervious surface, this is also impervious surface. So, in between this is a soil stratum. So, sometimes what happen, so here impervious layer could be, this is aquiclude, this is called aquiclude, where it cannot transmit or absorb water, this is also aquiclude. Okay. Or it could be aquifuse, right, aquifuse or aquiclude. Okay. So, sometimes you have aquitards, right. So, aquitards are kind of semi. Okay. So, in that case what happens? So, if there is a leakage, okay, so simply there is a leakage. So, that means it is not perfect impervious layer, and this is, so this kind of aquifer is called the leaky aquifer. Okay. So, leaky aquifer case, your leaky like a pervious surface could be on top or it could be on bottom. Okay. The pervious surface could be bottom or top, in both cases it will be leaky aquifer. So, if you observe this, so here and also the leaky aquifer could be a confined leaky or unconfined leaky. So, in this case leaky confined aquifer, so impervious and impervious, but still you see the leakage from the bottom to top. So, here unconfined aquifer you can still see the leakiness here. So, this is leaky unconfined aquifer. Okay. So, the next is if you overall see the all aquifers. So, this is the picture. So, let us say at this point there is a recharge is taking place. Since this is open to the atmosphere, so here this level is called a water table. Then from there the entire water will be flowing through the two impervious layers. So, then this is the confined aquifer, and if you drill hole at this point, right, the water which is confined under hydrostatic pressure is going to flow, right. So, here also if you drill hole to this and you get water level here, right. So, whatever this line we are showing, so that will be that will give the pressure head at this point and pressure. So, the pressure present in this confined aquifer, right. So, that is this is also called the piezometric surface or potentiometric surface. Okay. So, since this piezometric surface is above the top of the well, so it starts flowing continuously. Okay. So, here since the top of the well is more than the piezometric surface, the water level will be staying in the well. Okay. Okay, so, that is one thing, and above that, since these two are impervious surfaces, this is a confined aquifer, but above that, so there is again geological formation which has this is impervious surface bottom, and the top there is no impervious surface, this is open to the atmosphere. So, this and you can see the top of this geological formation called water table, because this is atmosphere intervention. So, if you drill hole at this point, so water level which is seen in this water is called water table well. This is a water table well or phreatic well. This is also called phreatic well. This is the artesian well, since it is connected to the confined aquifer. This is a phreatic well, okay, since it is connected to the unconfined aquifer. Okay. So, there is also you can also see the locally formed aquifer, that is a perched aquifer, and if you have connected to the tube well connected to this perched aquifer is perched water table well. Okay, right. So, this will show the aquifers and the wells, and then two surfaces, the water table and piezometric surfaces. Okay. So, the next is the same thing, piezometric surface I already explained. So, this is an imaginary surface which connects the all points the pressure in the aquifer, confined aquifer. This is the confined aquifer. Okay. And the elevation of surface at a given point defined by water level is penetrated into confined aquifer. Okay. So, similarly, if you see the water table I already explained. So, the water table basically connects the unconfined aquifer, and the water table, the pressure at the water table is equal to the atmospheric pressure. Okay. So, the recharge area here if you see which is the where the region which supplying water to the groundwater. For example, here this is the recharge point where it supplies the water to the groundwater. So, this is the recharge area, and the groundwater basin. So, this is a physiographic unit containing one or more aquifers. So, aquifers the whole topography can have one aquifer or more than one aquifers. So, that is called the groundwater basin, and the aquifers can be connected or interrelated. So, they can be interrelated. Okay. So, the next is the springs. Okay. So, the springs so when water flow naturally from the aquifer to ground surface is called a spring. Suppose, so there is a this kind of thing. So, there is a water which is infiltrating down, but you have you have impervious surface here. So, definitely that is going to pass through this, and this forms the spring. Okay, you can see. So, this forms a spring. So, there are different kinds of springs. The component of hydrosphere, if you see, this is a groundwater flow, right, in confined aquifer, and this is unconfined aquifer. So, the recharge which is going here, right, this is impervious surface, due to impervious surface. So, the water, some of water will flow through this and some water will flow through this, and there. So, this, since it is impervious surface, you can see continuously the water flowing, right, this is called a spring. So, the next, the types of springs could be like a depression spring. So, the depression spring where here the water which is infiltrating down will be, I mean there is a depression here, right. So, the depression is connected to the water table, right. So, the local water table, since there is a water connected to water table, and it is going to flow automatically, right, because there is a depression, right. And here there is a contact spring. The contact springs are like the high K. So, more water will infiltrate, and at the bottom there is a low K, right, and again high K. So, what happened here, the water which is infiltrating down cannot infiltrate in further layer. So, and that will be formed as a spring, okay, because and again there is a another layer which is high K. Okay. So, when the low K is sandwiched with two high Ks, so then you can have this contact spring. So, in the fourth one is the artesian spring. So, similar to the artesian spring case, suppose here it is a high K, right, and here also this is a low K, the low K and high K. So, water which due to high K, the water is going to pass through, because of the low K it cannot penetrate down, okay. And then here, from here, this is high K. So, water from here and here will be oozed out here from here, because it cannot enter through this, right. So, this is so the water I mean here the result from the water under pressure from confined aquifer, either at the outcrop of the aquifer or through the opening of the confining bed, okay. And the tabular fracture spring. So, sometimes what happens, there is a fractures, if you see, right. So, the water all fractures are interlinked. The water from this fracture, and finally, if there is a way out, right, all fractured water will be oozed out as spring. Okay. So, this is called fracture spring, the same thing here. Okay. So, the other these are the aquifer properties. If you see, the porosity is one of the properties, because it is a soil media, and void ratio another property. So, these properties are already explained in lecture number 3 of week number 1. So, you can go through that, and other ones are the effective porosity. So, the effective porosity is out of 100% of the porosity. So, how much is really participated in the flow process, groundwater flow process. So, or what is the percentage of porosity which is effectively used in groundwater flow. Okay. So, the portion of void space in the porous material through which fluid can flow. So, that is the thing, and if the portion that experiences the flow process, so that will experience the flow process, the other process may not be, okay, may not be experience the flow process. So, for example, if you have a pore here, right, this is a pore and a soil particle, sorry. So, this is the soil particle, and this is another soil particle, and you have pore, right. So, some portion of the pore will have fluid that will be flowing, the other stagnant. So, in that case the porosity is not 100%, I mean effective porosity is 100%, but effective porosity is not 100%. Okay. So, aquifer type, if you see limestone, the effective porosity will be 0 to 20%, and sand 25 to 50%, clays 40 to 70%, right. And so, next property is the permeability. So, the permeability is basically the media property, the sand property or whatever it may be. So, not the fluid property. So, here permeability is the measure of media's ability to transmit fluid under hydropotential gradient. So, if you have some gradient of flow, right. So, the fluid will flow from one place to another place. So, and then that is due to the property of the material or property of the material. Okay. So, that is called the permeability. So, the approximately the proportional to the square of the mean grain diameter. Suppose the permeability is expressed is equal to C d square. So, C is the dimensionless coefficient and the mean diameter d. So, it is expressed in Darcy. So, 1 Darcy is equal to 9.87 to 10 power minus 13 meter square, and it is the property of course, the soil or not the water property. Okay. And the next is the hydraulic conductivity. So, here the hydraulic conductivity it is again fluid as well, it is the property of soil as well as the water. Okay. So, it contains both fluid and solid property. So, that it is defined as the volume of water that moves through a porous medium in a unit time under unit hydraulic gradient through a unit area measured at right angle to the direction of flow. If you have the flow measured here, right, Q. So, the K, the hydraulic conductivity, which is equal to the Q, right, when it is measured through a 1 meter square or 1 unit area of cross section and then 1 unit of cross section. Okay. So, then and the unit gradient, suppose here the pressure and pressure, the difference, the pressure gradient is unit, then the flow is equal to the hydraulic conductivity. Okay. And so, this is first given, the equation is given by Darcy. So, Q is equal to minus K dH by dL into A. So, here the negative sign indicates the pressure gradient, which is the gradient of pressure, I mean pressure is decreasing towards the flow direction. If you see here the pressure. So, this is the setup, the Darcy setup. Let us say the soil sand column. So, input water is inputting here. So, water is initially this is completely saturated. So, water passed through this and collected here. So, this is Q. So, since it is equilibrium, so the Q which is going in will be same as Q coming here, but the pressures are different here. So, that pressure H 1 here and H 2 here, the difference in pressure. So, that is delta H, and the gradient is L, delta H by L, that is the gradient. So, since the pressure the flow rate, so this is H 2 minus H 1. So, H 2 is less, H 1 is more. So, that is why this negative sign is required in order to get the positive Q. Okay. So, so that way this equation will be used to estimate knowing the Q and knowing area of cross section and the gradient, you can estimate what is K. Okay. Yeah. So, and then the K value here, if you observe clearly. So, the K value, so as I said, it has both fluid as well as solid property. So, K, this is permeability, and rho by mu. So, these are the fluid properties. Okay. So, K has both fluid as solid properties. So, mu is dynamic viscosity and unit weight of water, K is intrinsic permeability. So, for hydraulic conductivity K, the is clay for clays 10 power minus 8 to 10 power minus 2. So, it is a big range, right. So, sand 2200, gravel 100 to 1000, sandstone 0.0012 to 1. Okay. So, hydraulic conductivity will be more in case of gravel and sand and less and very less in case of clay, right. So, that is water is very difficult to transfer or transmit in case of clay soils. Okay. So, with this is the in this lecture we mainly focus on some basic stuff on groundwater. So, what is geological formation, what is an aquifer, what is aquifuse, aquitard, right, and aquicloud. So, these are different kinds of geological formations which are present underneath, and also the different soil waters. Okay. And then the properties of aquifers, and we also studied what is the aquifer types like confined aquifer, unconfined aquifer, pursed aquifer, and then leaky aquifers. Okay. And then we also studied the water table and phreatic water table and piezometric surface, and also different wells based on their connection to the different aquifers. So, the well is connecting to confined aquifer, it is called artesian well. If the well is connecting to your unconfined aquifer, it is called phreatic well or water table well. If the well is connecting to the pursed aquifer, that is called pursed water well. Okay. So, thank you.